We present temperature dependence of activation barrier for coronavirus inactivation, based on protein denaturation. By definition, virus becomes inactivated when it stops replicating. The measurement of inactivation is counted in number of cells contaminated by the virus. I will present a theory for inactivation rate in relation to temperature. Despite difficulties, the Arrhenius model is still being used for describing transition rates, in particular inactivation rate. The inactivation rate denoted by K of T, which is the rate of transition from a native state to the damaged, denatured state, is fitted with two constants. A, which is the attempt rate of the reaction, and EA, which is the activation energy of the reaction, referring to the critical reaction that delays the transition. Studies on thermal inactivation is found for many viruses, but also enzyme molecules can be fitted to our Arrhenius model, as demonstrated in the case of alpha amylase. The striking phenomenon, that the slope depends on the solvent, is not well explained in our Arrhenius model. Following the COVID-19 pandemic, data on thermal inactivation of coronaviruses was assembled, and the rates seemed to fit approximately to our Arrhenius linear slopes. When the constants A and EA from these Arrhenius fitting are presented in a plot, the points sit on a single line, a phenomenon called the Meyer-Nelder rule. However, the funny thing is that A spans 25 orders of magnitude, only among different species of coronaviruses. This suggests that the constant A is actually not an attempt rate and does not represent a physical meaning. Therefore, we need to seek a new theoretical mechanism that explains the results. In fact, since Svante Arrhenius proposed his law in 1889, it has been established that the activation barrier is a free energy with entropic contribution rather than a fixed energy. Concerning coronaviruses, and possibly in general, thermal inactivation involves a certain protein denaturation. The transition of a protein from globule structure to random coiling restrains the entire inactivation process. The globule is the native and fully functional state of a certain polymer in the virus, possibly a critical part in the spike that is required for penetrating the host cell. The steps of the transition go along three reaction coordinates. Melting is a first-order transition, which involves releasing some of the hydrogen bonds by vibrations. This is not the rate-limiting step, since there is no change in free energy along the reaction. Also, the structure is mostly conserved after melting, so I believe the virus is still active. There is a second-order transition, along A to P, which is related to random coiling of the polymer that gradually dissolves the orderly structure. Although entropy drives the system toward random coiling, it is restrained by hydrophobic repulsion that keeps the structure more or less in place. Hydrophobic interaction is caused by a volume in the polymer that remains dry, where hydrophobic residues hide from the solvent. Significant change in polymer conformation should come on expense of exposing these residues to the solvent. We can invest energy and force the system opposite to the repulsion force, yet an easier way to break that forces is by leaking of solvent inside the dry volume of the polymer. The wetting of the polymer is thus a third reaction coordinate. After wetting, there is no longer hydrophobic repulsion, since the confinement to a dry volume is removed. If water are concerned, electrostatic repulsion between residues is screened by the solvent. The wet polymer is doomed to irreversible damage either by aggregation or by following the entropic drive toward a full denaturation. However, the penetration of water through small gaps is restrained by an entropy barrier. In essence, this step is hydrophobic collapse in reverse. The reaction coordinate A to P is also an order parameter of the transition to random coiling. This is a second-order transition, and thus the free energy as function of A to P and temperature can be described by the Landau theory. The form of dependence is shown, with two constants and a transition temperature Tm. Since the canonical form of the free energy is E-street, we identify the energy and entropy terms of the perturbation, caused by the order parameter. We can see that the plot of G as a function of A to P has a minimum at A to P0, where the system is at equilibrium. Equilibrium is due to the balance between entropic drive and the hydrophobic interaction, so the hydrophobic interaction is the elastic energy of the perturbation. In this description, the raise of temperature only causes a limited change in the polymer configuration, which remains reversible. Now, when adding the wetting coordinate, we can form a new expression for the free energy perturbation, following the overall transition. When the solvation state A to S is at 0, the formula is exactly like in the Landau theory. When A to S is 1, meaning that the polymer is fully wet, the first term disappears, since there is no longer hydrophobic interaction. The second term is then added, which accounts for the negative entropy contributed by the solvent. The third term is just the entropy of the random coiling. The free energy barrier is calculated as the maximum Ng minus the initial G at equilibrium, which is neglected, being a second order and T minus Tm. Delta G is then used to calculate the transition rate. So we end up with a formula that is a power law in T minus Tm. The parameter A tilde is a constant related to the native reaction rate, and U is an amplification constant that depends on the Landau parameters and describes how the transition rate increases with temperature. The inactivation time at certain temperature T can be calculated based on the amplification constant U and omega, which is the log of the reduction in population of active viruses. I am showing simulation of the theory with Landau parameters fitted to an activation rate of SARS-CoV-2. On the left is our result in a dry polymer, compared to a sophisticated molecular dynamics simulation by Maffei et al. That has some resemblance. However, in the state of eta S equals to 0, inactivation does not occur. In dry state, the elastic energy concerned with the transition increases with temperature, based on increase in the point of equilibrium eta P0. Now we apply the wetting influence. In a wet state, the said elastic energy disappears, since it originates in hydrophobic interaction. Thus, in the wet state, the energy dependence on T vanishes while entropy increases. It implies that the free energy barrier delta G decreases with temperature, while in comparison, for the Arrhenius model, the energy barrier is constant. This is the key difference in mechanism between our model and Arrhenius. The rate of the transition increases much more due to decrease in activation free energy G than expected in Arrhenius formula with a constant activation energy. Finally, we show how the theory corresponds to data collected on coronaviruses. The span of the constant of Arrhenius is shown in the first two columns. There is a huge range of attempt rate A. However, in our model the span of constants is reasonable. The variation in the native rate A tilde between virus species could be related to variation in redundancy factor, such as the number of spikes in a single virion. The power law form is a preferred one, and is accepted as empirical law in hyperthermia medicine. Actually, we can explain the Meyer-Nelder rule based on first-order expansion of the two formulas. The existence of transition temperature Tm is the missing link between the Arrhenius attempt rate and the actual native rate. We have studied the latest inactivation measurements of SARS-CoV-2 and fitted the results with the two laws. The difference in fitting is very small, but the basic mechanism is rather different. From the plot we predict that a human body temperature of 39 degrees Celsius, in which the patient suffers from fever, is actually helpful to diminish the active virus population by 4 orders of magnitude within 28 hours. For summary, the free energy activation barrier is of the form shown, with linear dependence of delta E over T on T minus Tm. That is based on the Landau theory of second-order transitions. Kt is proportional to U in the power of T minus Tm, similarly to accepted model in hyperthermia. The parameter span for inactivation of coronaviruses is rather narrow based on the new model. Fever, 39.0 is effective against the illness. 28 hours of fever should achieve 99.99% inactivation of the SARS-CoV-2 virus, 14 hours is expected to reach 99% inactivation. Further reading. Shahar, Seifer, Michael Elbaum, Thermal Inactivation Scaling Applied for SARS-CoV-2, Biophysical Journal, 2021.